So we're going to consider here the evolution of stars after they have been on the main sequence, before we deal with how they're formed. Much of our understanding of stars comes from making computer models of how a large mass of gas of typical composition behaves under gravity. It's found that all the main sequence stars are turning hydrogen into helium in their cores. The mass is what determines where on the main sequence a star is. Once a star of a given mass starts, it will more or less stay in the same place on the main sequence for a very long time. The luminosity and temperature of the star do not change much as the fraction of helium in the core increases. Eventually, however, there's going to be a shortage of fresh hydrogen in the core of the star. For our Sun, that time is about 10 billion years. For other stars, we can make use of the fact that the mass of a star is a measure of the total amount of fuel it has, and luminosity is a measure of the rate at which the star is consuming fuel. If we consider both these things, then, we see that the lifetime of a star is proportional to its mass divided by its luminosity. And since we know luminosity is equal to mass cubed, we know then that the lifetime of a star is proportional to 1 over the mass squared. The high-mass stars therefore have the shortest lifetimes. An O5 star might have a mass 40 times that of the Sun. That means its luminosity is going to be 400,000 times that of the Sun. In other words, it's 400,000 times brighter, or uses 400,000 times more energy per second. Even though it's a much bigger star, it's burning at such a faster rate that it's only going to last about 1 million years. Whereas a G-type star, say just a little bit above the mass of our Sun, so luminosity almost the same as the Sun, is going to last about 8 billion years. And a low-mass star, say an M star that's only got a half a solar mass, it's only 8% as bright as the Sun, but it will last, theoretically, 56 billion years. Now, stars evolve very slowly, so that generally we can study each star only at one stage in its life. We rarely see stars change, although later we're going to see that stars sometimes undergo a very sudden change at the end of their lives. We usually have no way of knowing how old a star is. Typically, all we know is its luminosity, temperature, and if we're lucky, its mass. We can suspect that a star can change its position on the HR diagram as it gets older and changes its composition, but we can't immediately tell which stars are older versions of others. For an astronomer, it's a bit like an archaeologist trying to piece together relics as a sequence of time. Since we cannot see inside stars to see what's going on, what we try to produce is theoretical stars that have the same properties of the observed ones, and this needs computers. Astronomers start with a ball of hydrogen and calculate how things like temperature and pressure at different positions inside a star change as thermonuclear reactions take place. In a star like the Sun, hydrogen fusion lasts for 10 billion years. The Sun stays on the main sequence, but it slowly increases in size and luminosity over that time. Now, the change is so slow that life on Earth is not affected by any of these changes. In about another 5.5 billion years or so, there's going to be so much helium ash in our Sun that no more hydrogen burning can take place. When that happens, there's no more pressure pushing out, so gravity starts to win, and the center collapses, and as it collapses and pushes together, the ideal gas law tells us it's going to get hotter. And as it gets hotter, the helium now starts to be converted by another nuclear chain, and that reaction makes carbon. Essentially, 3 helium nuclei go into 1 carbon nucleus. This reaction takes place very quickly, gives off a lot of energy, so that the luminosity of the Sun will increase comparatively rapidly. That extra heat causes the Sun to expand to a much larger radius, and it becomes a red giant star. This picture here shows, we haven't talked about what a protostar is. It's a star that's being born, and it becomes a main sequence star, and it stays there for a long time, and a star like our Sun, as it's burning helium, will become a red giant. Now, in its red giant phase, the Sun is actually going to be larger than the orbit of Mercury. So Mercury would fall into the sun. And it's going to look enormous in the sky, 50 degrees of angle across the sky. The temperature of the Earth would get so high that life would certainly be extinguished. Red giant stars tend to have very strong stellar winds, blowing a lot of gas back into the interstellar medium. In fact, mass loss is a major feature of the late stages of a star's life. Some stars in these late stages become variable. The balance between pressure and gravity is no longer stable. They grow and shrink with periods ranging from days to maybe many years. As the stars grow and shrink, they can change their surface temperatures, and therefore they move around on the HR diagram. Now, two important groups of variable or pulsating stars here are our Lyrae, which was first discovered in the constellation Lyra, and that has a mass comparable with the Sun's but 40 times the luminosity, and have periods of about half a day. And when we were talking about variable stars before, we mentioned the Cepheid variables, first discovered in the constellation Cepheus. More massive than the Sun, about 20,000 times more luminous, so we can see them from further away. And they have periods from 1 to maybe 70 days. The Mira variable stars are pulsating red giants, and the ZC Ceti are pulsating white dwarfs. What I want you to understand is they are variable stars. There's different types, and different types, the period that they vary is going to change. Why do they change? Giant stars pulsate because their atmospheres trap some of their radiated energy. That heats the atmosphere, which then expands, and as soon as it expands, it allows all that radiation to escape. That expanding atmosphere also cools, and so once the radiation escapes and it cools, it shrinks back down and to begin the process again. The higher opacity, the ability to trap radiation of a star's atmosphere, only occurs in a limited instability strip on the HR diagram. Now, many pulsating stars obey a law that relates their luminosity to the period of pulsation. The longer the period, the more luminous the stars. And the reason is larger stars are more massive and have less surface gravity. And so if I look at a graph then of Cepheid variable stars, and I plot all of them, I notice that they lie on this line. This is a logarithmic scale. You really don't need to understand it. Just know then that there's a relationship between the pulsation period and the luminosity. This is very crucial because it allows me to measure with a stopwatch the time it takes to pulse. And once I know that, then I know its luminosity, therefore its distance exactly.